All right, hello, back with the follow-up video for the non-calculator question, shall we? Let's rock and roll. So, we are looking at this graph of f. Let f be a continuous function. This is a question from the year 2021, number 4, just so we're all on the same page here. Let f be a continuous function defined on the closed interval -4 to 6. You can see it plotted there. The graph of f consisting of 4 line segments is shown above. Let g be the function defined by g of x equals 0 to 6 of f of t dt. All right, agreed. On what open intervals is the graph of f concave up? Give a reason for your answer. So, the let's jot this down here that g of x equals 0 to x of f of t dt. G of x equals 0 to x of f of t dt. And they want to know when or on what intervals is the graph of g of x concave up. How is concavity determined? With the second derivative, primarily, right? The second derivative test. So g of x, I'll write it one more time, is 0 to x is the integral from 0 to x of f of t dt. G prime of x is equal to f of x. Because if you recall, I'm going to write, not to confuse you with f and g, I'll use a lowercase. If, if a function is defined as the integral from 0 to g of x of f of t dt, the derivative is f of g of x times g prime of x. Okay? We know this to be true. So for this relatively simple integral here, where g of x is simply x, you take the top bound and plug it in, that's f of x, and multiply by the derivative of the bound. Well, the derivative of x is just 1. So g prime of x equals f of x. So that means g double prime of x, the second derivative, is equal to the first derivative of f. So g prime of x is concave up on what intervals? Well, whenever this is positive, whenever the first derivative is positive. Well, if this is the graph of f, the first derivative is positive wherever this graph is increasing. This graph is increasing from -4 to 2 and from 2 to 6. So g of x is concave up the on the interval -4 to -2 and the interval 2 to 6 because f prime of x is greater than 0. So even maybe more accurate, you could say because g double prime of x, which is equal to f prime of x, is greater than 0, right? Just to really hit that home, like, hey, I know what I'm talking about. The second derivative, which happens to be the first derivative of f, is positive, so therefore this thing is concave up. Cool? Hope so. Let's move on. Part B. Let P be the function defined by blah. Find P prime of 3. So I'm just going to make life easier so I don't have to write that out and paste that down here. So find P prime of 3. Now let's find P prime of x. First of all, what is P prime of x? This is a product, so we're going to have to use the product rule when deriving. So the derivative of this is leave the first function alone times the derivative of the second function plus take the derivative of the first function times the second function, right? Or you can switch that around. I don't know how you've personally memorized it, but it's just one of each, right? Derive, leave it alone, plus leave it alone, derive. All right? So p prime of x equals that. So that means p prime of 3 equals g of 3 times f prime of 3 plus g prime of 3 times f of 3. Okay, well, what is g of 3? G of 3 means we have defined, recall, that we have defined, or they defined, I should say, that g of x is equal to that. So that means g of 3 is equal to that, right? That's g of 3. So you're going to take the answer to this and multiply it by f prime of 3. Well, what is f prime of 3? F prime of 3 is the slope of f at x equals 3. So here's x equals 3. What is the slope of f? Well, the slope of this entire interval is up 1 over 1, up 1 over 1, up 1 over 1. So the slope is 1. So at this particular point, f prime of 3 is equal to 1. So that's just times 1. Beautiful. Plus g prime of 3. Now, in the previous problem, we took the time to say that g prime is f. So g prime of 3 is the same thing as f of 3, right? So this is really f of 3 squared, right? There's f of 3 times itself. So let's go ahead and find f of 3. F of 3 is negative 3. So this is negative 3 squared, or I'll write it out as negative 3 times negative 3. Now, we still have to do this part, and I'll have you know at this point, we're done with the calculus, right? Once we get this answer, we're done. So what is the integral from 0 to 3 of f? That is the ticket. That is g of 3. The integral from 0 to 3, this is a positive area, and this is the same triangle with a negative area. So those are just going to cancel each other out. And this area is 1, 2, 3 and a half. So negative 3 and a half, because it's below the x-axis. So negative 3 and a half plus 9, if you want to go ahead and multiply that together. Again, you don't even have to do that much, right? Maybe I should say what I've said before, right? Stop doing math, just and then boom, there it is. There's p prime of 3. If you kept going, theoretically, it works out to what? 5.5, right? Is that what it is? Yeah, 5.5. Negative 3.5 plus 9 is 5.5. Let's continue. Find the limit of g of x over yada yada. All right. Well, I'll go ahead and copy that and paste it down here. My blank. So, what's so hard about this limit? Well, you always want to simply plug in 2 first, right? Just plug in 2. So this is g of 2 over 2 squared minus 2 times 2 comes out to a 0 in the denominator, but is g of 2 0? Because if not, you can't use L'Hopital's rule. What is g of 2? Well, g of 2 is the integral from 0 to 2 of f of t dt. Well, what we just pointed out moments ago was these two triangles canceled each other out. So this positive area and this negative area would be 0. So it comes out to 0 over 0. So now we can use L'Hopital's. So the limit as x approaches 2 of g of x over x squared minus 2x is equivalent to the limit as x approaches 2 of g prime of x over 2x minus 2. I took the derivative of the top and bottom. So now when we plug in 2 times 2 is 4, 4 minus 2 is 2, we get a denominator of 2, and g prime of 2 is equivalent to f of 2. Because again, we've said this now in all three parts so far. We keep referencing the fact that the derivative of this integral is just f, right? So what is f of 2? F of 2 is 4. Oops, that's f of 0. Apologies. F of 2 is negative 4. So f of 2 is negative 4. And if you want to do it all the way, you get negative 2. To explain where the points are on this one, let's go to the scoring guideline. The points on this one is you use L'Hopital's rule, and then showing this work, it says answer with justification. Their justification is the work. I think there are probably a couple, maybe a little in between things that you could skip, but yeah. And to go back to the previous one, just for the sake of consistency here, in part B, there were 3 points to be earned. The first point was earned by correctly doing the product rule. The second point is earned by solving for g of 3 accurately or g prime of 3 accurately, interestingly enough. So either one of those, if you got negative 3 or negative 3.5, they're going to give you that second point. And if you found both, you're basically bound to get the last part right. And that's your third point, getting 5.5. But again, you don't have to literally write 5.5. All right, almost done here. This question is moving pretty quickly here. Find the average rate of change of g on the interval -4 to 2. Does the mean value theorem guarantee a value c between -4 and 2 for which g prime of c is equal to this average rate of change? Justify your answer. So the mean value theorem, and actually let me pull up my document. My explanations in our workbook, if you says, the basic definition of the mean value theorem is that the function has at least one point where the slope of the tangent line is equal to the slope of the secant line that connects the two endpoints. But more formally, and what you have to say is if f of x is continuous on the closed interval a to b, and it's differentiable on a to b, then there must exist at least one value c in a to b such that f prime of c is equal to f of b minus f of a all over b minus a. So we need to demonstrate that g, because again, the question specifically says it's talking about g, right? So f in this context is g. So we need to state that g is continuous and differentiable on this interval. We need to find the average rate of change. And if this average rate of change is between -4 and 2, well, then we've proven our point, right? So does the mean value theorem guarantee a value between -4 and 2? Let's find out. So again, I've got this justification, and it's not perfection, but I really did try my best here to say, like, to copy how they sort of like to write things on the scoring guidelines. All right. So how about I split screen this? so we can kind of see this at the same time, and you can see how I'm sort of constructing this. So the three big things: continuous, differentiable, and find the average rate of change. Continuous, differentiable, and find that average rate of change. Now, I'm saying continuous first, but they often tell you that it's differentiable, which then allows you to conclude that it's continuous. And the same is done in this problem. So it says, let f be a continuous function defined on the closed interval. The graph of f, consisting of 4 line segments, is shown above. Let g be the function defined by g of x equals blah, blah, blah. Well, we can say g of x is differentiable on -4 to 2 because g prime of x equals f of x. So because the derivative exists, we're saying it's differentiable, right? So because they told us what g is, and because we are capable of deriving it, that means the derivative exists. We've just demonstrated that. G of x is differentiable on -4 to 2 because g prime of x equals f of x. And therefore, g of x is continuous on -4 to 2. I'm looking at this left-hand side. So we didn't say it is given, but we said f prime of x equals g of x, therefore f of x is differentiable. Right? I kind of wrote my sentence backwards. I apologize for that. It was just what naturally came out. So could have, should have, whatever. G prime of x equals f of x. Right? It's all saying the same thing. And therefore g of x. But this, you want to say the differentiable part first, because then because differentiability implies continuity, right? You don't want to say the continuous part first. You want to say the differentiable part first, 99 times out of 100, because it allows you to conclude the continuous part. And because we've got that, right, now let's do the math and find the average value, okay? So let me actually go ahead and put this in the correct blank. Let's find the average value. So we want to find g of 4. I can go full screen for the moment on this. G of 4 minus g of -2 over 4 minus -2. Is that right? It's -2 to 4, right? Oh, -4 to 2. Sorry, -4 to 2. Okay, so what is g of 2 and what is g of -4? We need to find the average rate of change. That's what we're doing right now, right? Because the mean value theorem applies. The mean value theorem works for this function because of the setup. But now we're getting into the nitty-gritty of, does it make this true, right? And we just need to simply demonstrate that the average rate of change falls between -4 and 2. That's all we need to do right now. So we just need to find the average rate of change. So we know g of 2 is 0. That was something that we had to do earlier. So g of 2 is 0 minus, what is g of -4? G of -4 is going to be 0 to negative. Well, 0 to -4 is this area except negative, despite the fact that it's above the x-axis because the bounds are in the reverse order, right? So what is the area of this region? and then make it negative. Well, this would be 1, 2, 1, 2, 3, 4, 5, 6. So this is 6. 6 times 2 is 12 divided by 2. And then this is a little half. Actually, let's do this whole triangle. That would make more sense. This area is 2. And then this is 1, 2, 3, 4, 5, 6, 7, 8. So this area is 16. Negative 16 is the answer to g of negative 4. So we end up with negative 16, which is positive 16 over 6. Now, positive 16 over 6. So let's take the phrasing of the question, right? So what have we just demonstrated? What does the mean? I'm making this question longer than it needs to be. And hopefully you're like, Mr. Skis, just move on. I'm sorry. I know the mean value theorem. I'm rambling now. Oh my gosh, sue me. I'm sorry. But when we took the practice test on April 8th, there were 26 of us. I appreciate every single one of you. I keep saying that. I just really am so thankful that so many of you came out to that. But there was a question about the mean value theorem, and it wasn't really answered very correctly. There was also one about intermediate value theorem, and not too many answered that one correctly. But that's not what we're talking about. MVT, what are we saying? Because it's differentiable and because it's continuous, this value must exist. That's what we're saying. This value must exist on the derivative. It has to. The derivative must have this value. So, is that value between negative 4 and 2? Yeah. 16 divided by, oh, no, it's not. That's greater than 2. Wait, I thought the answer was true. Did I make a mistake? Oh, no, I'm crying. Oh, okay. Pausing real quick, sorry. Okay, so some of my phrasing was poorly phrased, and I apologize. C is not the output, it's the time. It's the time. And some of you probably knew that, and you were like, Mr. Skews, your phrasing's a little off. I'm sorry. So we're not saying that 16 over 6, which is 8/3, by the way, is between negative 4 and 2. We're saying that at some point along this interval, this value must exist. So to take the phrasing and to turn it into an answer, right? That is a really good strategy, by the way, to take the phrasing and turn it into an answer. I'm going to go ahead and copy this and then write my beautiful sentence. So let's copy this and turn it into a beautiful sentence. So what we're saying is, so we've got this, check, that's part 1. We've got this, check, that's part 2. Thus, so yes, the mean value theorem guarantees a value C between negative 4 and 2 of 8/3. I think that's all you got to say. So we said it's differentiable. We said it's continuous. We found the value. It exists. The fact that it exists means that we can guarantee that it's going to equal 8/3 along this interval. So their exact phrasing that they said is, yes, g prime of x equals f of x. So yes, g prime of x equals f of x. So g is differentiable on the interval negative 4 to 2 and continuous from negative 4 to 2. Therefore, yes, the mean value theorem applies. Oh, mean value theorem. Oh, we said guarantees. Guarantees a value C between -4 and 2. And they were a little fancier with such that g prime of c equals 8/3. And to read the nuances here, what was a short question I've now turned into a forever question, and I'm sorry. I hope you don't hate me. I always get so self-conscious about how I ramble. I'm sorry. To earn the first point, a response must present at least a difference in a quotient. So this is going to get you the first point, just getting the value. The second point could be earned without the first point if the response has the correct setup, but an incorrect or no evaluation of the average rate of change. The mean value theorem need not be explicitly stated, provided the conditions and conclusion are stated. Interesting. Okay. All right. Appreciate your time. Ta-ta for now.